The previous two sections that we discussed were very much about area under a curve. Section 5.1 was specifically that, and then Section 5.2 was the definite integral and how it's related to the area under a curve. You learned about the linearity properties of integration, or linearity properties of definite integrals, and some other properties. And so now we're kind of going to shift gears theoretically, but not so much notationally. The notation in section 5.3 is very similar to that of 5.2, but I want to emphasize here before we even discuss what an antiderivative is, that the process of finding a definite integral is a process which results in a number, an area or assigned area under a curve on an interval. The process of finding an antiderivative results in a function. They're different processes. And in the next section, I believe it is section 5.4, we see that those two very different processes are actually linked by the fundamental theorem of calculus. So, the first definition of section 5.3 is that of an antiderivative of a function. And I've at times made a big deal about preserving case in variables as they're given, like uppercase or lowercase, and it's critical in this definition. A function capital F is an antiderivative of the function lowercase f on an open interval from a to b if, when you take the derivative of capital F, you get lowercase f for all x in the interval. So I think of differentiating as a process of sort of going down, and antidifferentiation as a process of going up. And if that notion helps you, then that's great. If not, just line your waste paper basket with it. But when we take the derivative of the antiderivative, we should recover the function f. That's essentially what that part right there in the definition says. So, for example, if our function f is the function 1 over x, then what function could we specify to be capital F so that when we take the derivative of capital F, we get lowercase f? So what function is it that when we take the derivative, we get 1 over x? And you're at home watching these videos, feel free to press the pause button so you can actually give it some thought. One option for capital F would be, capital F could be the natural log of x. If we look at the derivative of the natural log of x, f prime of x, capital F prime of x, is 1 over x, and that's equal to f of x. Another option would be, maybe we could have capital F of x be something radically different, like the natural log of x plus 2. Then when we take the derivative of capital F, we get 1 over x, plus when we take the derivative of the constant 2, we get 0. So that is still equal to f of x. So we found that either natural log of x or natural log of x plus 2, those are both antiderivatives for the function little f, which is 1 over x. Because when we differentiated either of these two, we got 1 over x, which is lowercase f. Another example to build our intuition, and I just named this example because you've differentiated polynomial terms quite a bit. If f of x is equal to 3x squared, think for a minute about whose derivative that is. So if you could figure out whose derivative little f is, then capital F would be the antiderivative of little f. And so think about every time you've ever applied the power rule to x cubed. You bring the power down front, x to the 1 less power. This guy right here is the derivative of x cubed. So capital F of x could be just straightforward, plain old x cubed. Or capital F of x could be x cubed plus 79. right? I mean, why add that ridiculous constant? Because I can. When I take the derivative of capital F in this case, I get 3x squared plus 0. So the derivative of capital F is equal to little f of x. And this one would be for all x in the real numbers. The first example would be for all x in the positive real numbers, perhaps, because that's where we don't have to adjust the input for the natural log. Okay, third example. And this one we might have to think a little bit harder. The first two were exactly somebody's derivative, as we've applied rules a lot. What about if f of x is equal to cosine of 2x? Then what could capital F be? And again, remember, you're asking yourself, whose derivative could that be? And so at a first glance, it looks like capital F of x could be, well, whose derivative is cosine? Cosine is sine's derivative. And it's not just plain old sine, it's sine of 2x. And so if we had capital F was the sine of 2x, what would the derivative be? Well, this is one of those very simple but still chain rule applications. If we were to take the derivative of capital F, we'd get cosine of the inside function. So cosine of 2x times the derivative of the inside function, so we'd have to multiply by 2. Well, that's not what little f is. It's just plain old cosine of 2x. Well, what should we build into this capital F function to knock out that factor of 2 that we get when we differentiate? We just need to build in a factor of 1/2. And so once you've done your undoing of differentiation, you don't have to just be satisfied that your guess is accurate. Actually compute f prime of x. If you think this is what the antiderivative of little f is, differentiate it. The derivative, so bring the constant, using the constant multiple rule, constant out front. Now we're doing the derivative of the outside function, which is cosine of 2x, times the derivative of the inside function, which would just be 2. And the 2's cancel just like we designed them to do. So you're undoing the process of differentiation. Just to summarize the general notion of what anti-differentiation is, the process of finding an antiderivative is like being given a function, 1 over x, or 3x squared, or cosine of 2x, and saying, guess whose derivative I am? And we're not really just guessing. In fact, we're going to formulate some fairly precise rules to help us out with this.